accidentally copied my calculus notes today into my statics notebook. It's multivariable function time. For most of our math careers, we have been dealing with functions with one variable. You plug in something and you get something out. But now we're going to start plugging in two things and getting one thing out. We had already gotten an introduction to this before, specifically with sketching spheres and quadric surfaces. We now notice that we need to plug in two things in order to get one thing out. Or, God forbid, plug in three things. Also, I'm not going to be studying for public policy during this video. I did some during my spare time today, and I'm very confident on the material, so it's better going over the new stuff from today. This may be a horrible decision. A quick reminder, we can graph these multivariable functions by drawing trace lines. From now on, I'm going to refer to those trace lines as contours. We see that if we set f of x comma y equal to a constant, that we are going to get increasingly large circles centered at the origin. This is because the standard form for a circle is r squared plus x squared plus y squared. As you increase the constant that the equation is equal to, you are going to increase the radius. In 3 dimensions, this is going to look like a funny looking bowl. We call this an elliptic paraboloid. Let's start looking at the domain of these multivariable functions. Now, I don't know why quite yet, but apparently it is easier to do calculus with multivariable functions when you are dealing with the interior domain. The interior domain is basically the entire domain without the most extreme points. Since this thing is under the square root, we know that for it to be defined, that the inside of the square root needs to be greater than 0. It can also be equal to 0, because root 0 is just 0. So this has to be greater than or equal to 0, which means that x squared plus y squared has to be less than or equal to 1. So this is going to be where our multivariable function is defined. But we want the interior domain. Here is what a sketch of the domain of this function looks like. We notice that the circle is both solid lined and colored in. The domain includes everything inside the circle and the edges of the circle. The interior domain is going to be non-inclusive. We're going to take away the inclusive sign on this greater than symbol. The interior domain is going to be x squared plus y squared is less than 1. If we sketch the interior domain, we notice that the inside of the circle is still included and shaded in, but the outside of the circle is dotted, signifying that it is not included in the interior domain. Again, this is supposed to make calculus easier later on down the line. How? I'm not quite sure yet. I'm just going to trust the professor on this one. My stomach is starting to get grumpy and is reminding me that I have neglected to grab dinner. I'm going to take a quick break. I'll be right back to finish this calculus study. My hunger has been satiated. Let's get back to calc. We know that this equation is going to have a domain of all real numbers in the R3 coordinate system. So what would happen if we were to set this thing equal to a variable? Something pretty funky, it turns out. Since we have set this equation equal to a variable, we now have 4 variables overall, meaning that this thing has 4 dimensions instead of 3. We are never going to actually be able to plot this thing fully, despite this being the equation for a finite sphere. Because for every new w, there is going to be a new, larger sphere. They're just going to keep building on top of each other like a great nesting doll of calculus. That does not sound very fun. So since this thing is in 4th dimensions, we can draw its contour lines, which are going to be 1 dimension less than the entire graph, so 3 dimensions, but we will never be able to draw the entire thing. Finally, we can convert Cartesian coordinates into polar coordinates and polar coordinates into Cartesian coordinates. X is equal to r cosine theta, y is equal to r sine theta, r is equal to x squared plus y squared, and finally tangent theta is equal to y over x. This is just an exercise in plugging things into other things. Converting polars into Cartesians is a little bit different. R squared is equal to x squared plus y squared. Sorry. They sound like they're having fun. Let's say that we want to convert this polar equation into a Cartesian one. We have these equations up here. Let's use our trig rules to break this thing down. This is equal to 2r squared sine 2 theta cosine 2 theta. And then we can use our double angle formulas to break these things down even further. This is now looking a little bit familiar to us. Starting to look like what we have up here, but we are missing a key component. Remember, we are going to need to distribute an r. Is that r to the r power? I don't remember writing that. Remember, in order to get this into x equals r cosine theta, we're going to need the r. And that means we are going to need an extra r squared because we can only distribute this r squared to one of these. But this is easy to solve. We just multiply by r squared over r squared, which is, of course, equal to 1. And now we have this in terms of things we know. After we plug everything in and do the algebra, we get that this equation is going to be 4xy times x squared minus y squared over x squared plus y squared. My dumbass thought this was r to the r power. It wasn't. It was r squared. Something I had specifically corrected earlier in the video. Trust no one, not even yourself. On to statics. And I don't even need to get another notebook. Ha! Today we started learning about 2D structures and what moments of force they can support. When we're asking if a structure can sustain a moment of force, we're just asking if we push against it in a certain direction or pull against it in a certain direction, is the structure going to push or pull back? For example, if we have a roller right here, it can sustain a moment of force that is running upwards from the surface it is in contact with. But if we were to push against the roller from this side or this side, it couldn't sustain the moment of force, we wouldn't get any pushback, so it would roll. Quick disclaimer, we're also assuming that most of these cases are frictionless. I say most, you'll see why. A rocker can sustain the same moment of force as a roller, as can a surface without friction. A short cable or a short link can both sustain the same moment of force. It is going to be a force with a line of action running parallel and on the cable or link. A collar on a frictionless rod and a frictionless slot can also sustain the same moment of force. It is going to sustain any moment of force that is acting perpendicular to it. So if the moment of force is acting perpendicular to this rod, or it is acting perpendicular to this slot, they can be sustained. A pin on a hinge and a rough surface can both sustain a moment of force with x and y direction. With a friction surface, there is a limit on how much force that it can sustain in an x direction. That may factor in, I don't know. But right now, we just need to know that both of these cases can sustain a force in both the x and the y direction, or a force with an angle out. Finally, let's say that we have an object that is fixed in place. An object that is fixed in place can sustain both a moment in the x and y direction and a rotational moment of force. So a fixed situation can sustain the most moments. A rigid body is in static equilibrium if the force is in the x direction, the force is in the y direction, and the force is in the z direction, and, I forgot one, the moments of force are all equal to 0. For now, we're just going to be dealing with rigid bodies in 2 dimensions, so we're going to table f sub z for the sake of our own sanity. Unfortunately, I won't be able to get to any examples of this tonight. I definitely will tomorrow, but I have around half an hour left, and I would like to get at least some physics studying in. So let's go, shall we? I'm going to give the briefest of rundowns of capacitance. Capacitance is defined as charge over electric potential. It is written in SI units of farads, where 1 farad is defined as 1 coulomb per volt. If we find the potential difference across 2 objects and we find the charge, then we can find capacitance. And capacitance allows us to do several really cool things. The total energy being stored in a capacitor, where a capacitor is just 2 oppositely charged surfaces with some potential difference running across them, is going to be equal to the charge in those surfaces, Q squared, over 2 times C, or it's going to be equal to 1/2 C times the potential difference squared. We can also use capacitance to find electrostatic energy density, U sub E. U sub E is equal to 1/2 epsilon naught E squared, which is also equal to U, the total energy in the capacitor, divided by A times D, where A is the area of the two plates of the capacitor, and D is the distance they are apart from each other. Yeah, it's just going to take some examples for me to get this. The equations that they're adding on here don't seem that complex. We don't need to take any more integrals or find any new derivatives like we did when we were finding the electric field from the electric potential. I had never seen partial derivatives before that. That was the first time I had ever even learnt of their existence. This seems pretty tame by comparison. But I think that's going to be about it for the night. I'm very glad that I covered this before I left tonight. So public policy midterm tomorrow, I'm feeling pretty good about it. Of course, every single time I say that, things go horribly wrong. But tomorrow is when we break the streak. But in the meantime, thank you all so much for watching. See y'all tomorrow.